All right, so now we're going to talk about spherical coordinates, which is another way to describe points in three-dimensional space. And we'll see oftentimes with double and triple integrals, we may want to actually integrate something in terms of spherical coordinates rather than rectangular coordinates. As the name implies, spherical coordinates work really well if you're integrating something that has something to do with a sphere. And so, for example, here's a sphere and there's a point on this sphere, X, Y, Z. You can probably imagine how to get there. You would go over X on the X-axis, over Y, and then up Z. But another way you could think about getting to this point, X, Y, Z, is by, imagine you're at the origin and you're facing upwards towards the positive Z axis. So you're facing up here. You could rotate, actually, I think I'll do this. You could also be facing the, remember, theta equals 0 is also facing the positive x-axis, just like trig. So probably what would make more sense is you would rotate yourself a certain angle, this angle right here, so that you were basically facing the direction of that point. You're just looking at the equator instead. So that's an angle theta. So now you're looking there. And then let's go back to now you're facing this direction, but you're looking up to the positive Z axis. So you would then move your head down a certain angle. So I'll draw this right here. If you're facing up the positive Z axis, this angle we move down, we're going to call that phi or phi, depending on how you want to pronounce that. And then you're facing precisely this point, but you're still at the origin. So you would move this distance from the origin to your point, and we'll call that rho. If you think about it, those are the three variables. Two of them are angles and then a distance that could locate any point on a sphere, or really any point in three-dimensional space. So precisely phi or phi, heard it pronounced both ways, is the angle from the positive z-axis. So if phi equals 0, then you're facing up on the z-axis. That's your default. Theta equaling 0 is facing the x-axis. That's normal from trig. The angle and the angle we form is by moving counterclockwise towards the positive y-axis. That's theta, and then rho is the distance from the origin to the point. Just like with cylindrical coordinates, sometimes we might have to go back and forth to get from rectangular coordinates to spherical coordinates and vice versa. So I tried to draw this. Here's the X, Y, Z axes. I think there's a similar picture in your textbook, but try to follow this. This is a triangle here on the XY plane. If I go over X, over Y, in the XY plane, there's our angle theta, which is one of our parameters in spherical coordinates. And we know this distance right here is R. That's the same for cylindrical coordinates. But then to get some elevation here, we also had this triangle here formed by moving this angle phi from the positive Z axis. And this is our rho. So this would be Z. Notice this distance would still be R. You're just going this direction from somewhere up on the z-axis. And of course, that's z as well. So using these pictures, I can see from this triangle up here, the sine of phi is opposite over hypotenuse. So that is r over rho, opposite over hypotenuse, which means r itself would be rho times the sine of phi. And that's going to become important. The cosine of phi, cosine is adjacent over hypotenuse, so that would be z over rho. So if I multiply that over, z is equal to rho cosine phi. We already know from polar coordinates that our conversions for x and y in polar coordinates, for x it's r cosine theta, and for y it's r sine theta. So combining those two, if I want a conversion from x, y, and z into spherical coordinates, I know that x is equal to r cosine theta, but I also know that r is equal to rho sine phi. So if I multiply those together, this will be in for r, x is equal to rho sine phi cosine theta. For y, same thing. I'm going to steal this r for this value for r here. So y will be rho sine phi sine theta. And we already solved for z right here. We have that rho z is equal to rho cosine phi. So these conversions will become important. You should probably know them, or better yet, be able to reconstruct this picture and derive those in case your memory fails you. So as an example, more examples. So let's convert the rectangular coordinates 0, 1, 1 to spherical coordinates. And we have some conversions, but let's see if we can do this. Where is the point 0, 1, 1? This is meant to be x, y, z. That is, don't go in the x direction, go 1 unit in the y direction and 1 unit up. There's the point 0, 1, 1. This is 1, this is 1. So now think about how to get there in terms of my parameters rho, phi, and theta. So let's start with theta. Remember, your default is facing this direction, positive x-axis. So I want to face towards this direction. So I'm going to have to rotate theta equaling 90 degrees. That's pi over 2. Now I'm facing the correct direction. Rho is the angle from the positive z-axis. So I want to measure from there and rotate until I'm facing that point. And hopefully you can see, because this is 1 and this is 1, that angle for phi is pi over 4. And then finally, my distance that I would have to move, well, we'd happen to have a right triangle here. 1, 1, do the Pythagorean theorem, and you can see that rho should be equal to root 2. So those would be the parameters if we were to convert this to spherical coordinates. I guess we would have, well, we have them right there. Rho would be root 2, phi would be pi over 4, and theta would be pi over 2. Say you had a description of a point in spherical coordinates and you wanted to locate that in x, y, z coordinates. So let's start with theta. Let's start with this one this time. Phi is equal to pi over 2 because that's the angle from the positive z-axis. So if phi is pi over 2, that means I'm rotating, let's go this direction. I'm rotating 90 degrees. That's going to put me, whoops, that's phi. That's going to put me right here on the xy plane now. And then I'm going to rotate theta equals pi. That's going to take me around a half a circle. So I'm actually going to go over here towards the negative x-axis. This is negative x. That's an angle of pi. And then if rho is 3, that means now I've moved down here, moved over here. I'm going to walk 3 units out here, and that's going to take me to the point because I'm going in the negative x-axis, negative 3, 0, 0. And you can, okay, this one you can confirm using our coordinates, using our conversion system, right? We had x was equal to rho sine phi cosine theta. So if I wanted to do it algebraically, I could say it's 3 sine of pi over 2 times the cosine of pi. That's 1, that's negative 1. So I'd get negative 3 for x. Y would be equal to 3 sine of pi over 2 times the sine of pi. But because the sine of pi is 0, this comes out to be 0. And z would be equal to rho cosine of phi, which was pi over 2, and the cosine of pi over 2 is also 0. So you can get those points that way as well. Finally, before we jump into an integral here, remember we talked about in cylindrical coordinates, our unit for dv was r dr, r dz dr d theta. And in spherical, it's a little bit worse. our little tiny unit of volume, if you can imagine like just punching a little tiny hole out of a sphere, a little sort of ice cube shape, but from a sphere, you would have some curvature along these walls, along all the walls, really, except for these. This would be a small increment in the radius of the sphere. That would be d rho. This would be rho d phi, and it can be shown that this dimension here would be rho sine phi d theta. And it kind of resembles a cube. So if you, at a microscopic level, it would sort of be a cube. So if you just multiply length times width times height, what we get for dv, there's going to be two rows. So rho squared sine phi. And usually we would go d rho, d phi, d theta. Rho squared sine phi, d rho, d phi, d theta. And kind of like in polar, things get more complicated if you don't do it in this order. If you switched around the theta and the phi, you maybe have to think about it a little differently. Definitely if you switch the angles and don't do rho first, it's going to get more complicated. So usually this would be our default unit for dv. Okay, so let's do a problem. If you looked at the cylindrical coordinate video, we did an ice cream cone volume, and this one's another ice cream cone. But this time our ice cream cone is formed from the cone on the top and the top half of a sphere. So you may remember this cone looks something like this, going upward. And if I just looked at the top half of this sphere, you would imagine the sphere would come over the top here. Perhaps I should extend that a little bit and, come down to the ground. But the part I'm interested in would be this part right here. So this would be the equation of my cone, z equals the square root of x squared plus y squared. And here is, so I'm only using the top half. So what I would have to do for z, move the x squared, y squared over and take the positive square root. So it would be the positive square root of 9 minus x squared plus y squared. If I was doing it in cylindrical coordinates, you could probably imagine replacing these with r, right? That's r squared, that's r. But because this has to do with a sphere, it's actually much, much easier. If you think about how do you locate any point within this ice cream cone, notice that what a sphere is, every point on this sphere is 3 units from the origin. So the equation of a sphere in spherical coordinates is actually just all of the points where rho is equal to 3. So that becomes just like a circle in polar coordinates is just r equals a number. A sphere is just rho equals a number. Now, similarly, a way I can describe this cone is if my cone shape is z equals the square root of x squared plus y squared, if I put my conversions in, recall the conversion for z was rho cosine phi, and if this is really r in polar coordinates, r in spherical coordinates, we decided that was rho sine phi. You could cancel the rows out, and if you think about all of the points where cosine of phi equals sine of phi, that is pi over 4. So what this is saying in spherical coordinates, you could describe a cone like this, because what it is this cone makes an angle of pi over 4 with the z-axis, and you rotate all the way around. So every point on the cone is just pi over 4 away from the z-axis, and you just rotate around. So to get the volume of the solid, volume, I'm going to do a triple integral. Again, your unit of volume is always rho squared sine phi d rho d phi d theta. So I got to put limits on rho, phi, and theta. And so you think about this. For a given row, a random, not row, a random phi and a random theta. In other words, remember phi is pointing upwards normally, but so if I move it away from the z-axis, where does my rho go from? So for a random angle phi, rho, this distance is from 0 to 3. Do you see, no matter where I am, it's always from 0 to 3 because the equation of the sphere is always 3 units away from the origin. So it's just rho equals 3. So that makes it easy. Rho goes from 0 to 3. Phi, as I mentioned, would go from 0 to the biggest angle here, which we know now is going to be pi over 4. And as long as I have theta swinging all the way around the z-axis, going from 0 to 2 pi, then if I have phi go from 0 to pi over 4, I'm going to hit every single point in that cone, right? Imagine, if you move out a certain rho distance at a certain angle phi, as long as theta is spinning around the whole thing, you're getting every single point at that angle and at that distance, right? So you can imagine for any given row, you're getting a bunch of different cones, right? But if you do that throughout the whole region, you're getting the whole volume of the entire solid. All right, so let's work this out. So my first integration is with respect to rho. So sine phi is constant. So I'm going to have 0 to pi, 0 pi over 4. Rho cubed over 3. I didn't leave room. This is constant, so you can just leave it there. I'll just still keep it in front. But I'm going to evaluate this from rho equals 3 to rho equals 0. If I plug in the 3, I get 27 over 3, so that is 9. And then, of course, if I plug in the 0, I get nothing. So now we're just integrating 9. Sine phi. The 9's a constant. If you want, you can bring it all the way out of the integral, which I think I'll do. Antiderivative of sine of phi is cosine of phi. Negative cosine of phi. Evaluated from pi over 4 to 0. So let's take the negative out too. So that'd be negative 9, because that's a constant. And then if I just plug in, I get cosine of pi over 4 minus cosine of 0. Which is root 2 over 2 minus 1. Which is a number. I guess you could just, you could bring it out here as well, but we're just going to integrate that with respect to theta. So we'll end up with negative 9. Yeah, let's go ahead and pull that out. Root 2 over 2 minus 1 theta from 2 pi to 0. If I plug in the 2 pi minus the 0, I just get 2 pi times that. So it'll be 2 pi times negative 9 root 2 minus over 2 minus 1. I was a little bothered that this might be negative, but I think root 2 over 2 minus 1 is negative. So when I multiply that by negative 9, this will be a positive number. I'm sure we could rewrite it, but we'll just live with that. You can probably, if you want to, try to imagine what that would look like trying to integrate that solid in cylindrical coordinates and even rectangular coordinates. And I think you would find it's much more difficult. Generally speaking, solids that have something to do with spheres are going to be easier to use spherical coordinates. than cylindrical or rectangular coordinates. Okay, one more problem here, continuing on one of the more recent topics was finding centroids. So here we're going to find the centroid of the portion of the sphere, a unit sphere, in the first octant. So this sphere has a radius of 1, so it intersects the x-axis at 1, y-axis at 1, z-axis at 1, and it's just the portion in the first octant, so it might look something like this. So if you can imagine the solid, this is the solid we're finding the centroid of. Like I guess you could, it's about an eighth of the sphere if you think about it, right? There's 4 sections like this above, and then the bottom half of the sphere would have another 4 sections. So we're looking for the centroid. Remember, the centroid means the density is constant. If they density constant, it's the center of mass with a constant density. So it's like the balancing point, the middle point of this solid here that we're trying to find. And once again, by symmetry, I think we could agree that if we find one of the coordinates, so we're looking for an x bar, y bar, z bar, but it would seem to me, since this looks the same in all directions, that by symmetry, they're all going to be the same. All the same. So let's go for x bar. So x bar is the moment about the YZ plane. If you haven't seen the video on finding centers of mass, you might want to go back and look at that. Divided by the mass. And of course, the mass is the density times the volume, and we're pretending the density is constant. So why don't we just, and we could find the volume of this, again, if we recognize this, the volume, this is 1/8 of a sphere. And the volume formula for a sphere is 4/3 pi r cubed, but my r is 1. So it's really pi over 6. That's my volume. So we've got the denominator here. Let's find the moment about the YZ plane. And that's defined to be the triple integral over the volume of the solid, where we multiply the distance to the YZ plane, and the distance to the YZ plane is x. So it's x times density times dv. Okay, now we have to do this in, well, we want to do this in spherical coordinates because this involves a sphere. So we need to use our conversion for x. Our conversion for x, go back to the first page, is rho sine phi cosine theta. Density, we'll just pull that out. That's a constant. And for dV, our standard unit is rho squared sine phi d rho d phi d theta. Putting limits on this. This is a sphere of radius 1, so any point, to get to any point on here, all I have to do is let rho go from 0 to 1. Phi is the angle from the z-axis, and so to get from here to here, that's only rotating pi over 2, sorry. So phi is going to go from 0 to pi over 2. And theta is how much you have to swing your angle from x to y to get to this whole region. So that is also pi over 2. So this is looking like a pretty serious integral here. So density If I clean this all up, so 0 to 1, I'm going to have rho cubed sine squared phi cosine theta d rho d phi d theta. So my first integration, these are constant, so it's just going to be rho to the fourth over 4. I'll just leave these here, sine squared phi cosine theta. Evaluated here, I'll just put it from here. This is going to get evaluated from 1 to 0. Whoops, we already did d rho, d phi, d theta. Because these are constants, so it doesn't matter. That's just going to give me 1/4. I'm going to pull that 1/4 out. So now I have delta over 4. And my next challenge is to integrate sine squared phi with respect to phi. And you may remember, in order to do that, you need an identity. This is a 21b thing. The identity for sine squared is 1/2 1 minus cosine of 2, in this case 2 phi. I mean, here's another thought too. What I've been doing when I'm holding this constant, because I'm integrating with respect to phi, and before I just kind of left it there. Well, if it's a constant, it could actually come out at least of the first integral, right? I may have to integrate that with respect to theta, but just to get it out of the way, let's just move this right here, right in between, cosine theta. That's coming at the very end. So 0 pi over 2, cosine theta is there. Let's distribute this to see how it's going to integrate. 1/2 minus 1/2 cosine 2 phi. Okay, antiderivative 1/2 phi minus, remember, cosine of 2 phi is going to integrate to sine of 2 phi over 2. There's going to be another over 2, and there's already a 1/2 there. So when all is said and done, it'll be 1/4 sine of 2 phi. So if I plug in pi over 2, this is going to turn into pi over 4 minus, notice when I plug in the pi over 2 here, this is going to turn into pi, and the sine of pi is 0. So this will be pi over 4 minus this will be 0. And then, of course, if I put the 0 in, that'll be 0. That'll be 0. So pi over 4, I might as well write it out, minus 1/4 sine of, that'll end up being pi, minus 0 minus the sine of 0, which is also 0. That's 0. Another piece of paper. So then we have delta over 4. All of this is just going to be pi over 4, so I might as well bring that out. And then I just have to integrate cosine of theta from 0 to pi over 2. Delta pi over 16. This will integrate to sine of theta from pi over 2 to 0. Sine of pi over 2 minus sine of 0. Sine of 0 is 0. This is 1. So finally, I get an answer of delta pi over 16. There we go. So putting that all together, remember we had x bar was the moment about the x-axis times over delta times the volume. So x bar will be delta pi over 16 divided by delta The volume we came up with was pi over 6. Those cancel, actually the pi's cancel too. And if I flip and multiply, I get 6/16, which is 3/8. And so, as we also agreed by symmetry, x bar, y bar, and z bar would all be the same. So our centroid is 3/8, 3/8, 3/8. Kind of interesting that this has to do with a sphere. I've kind of expected pi to be in the answer, but there isn't. It's not in our answer, but. And you can see this is kind of what is typical in 21D with triple integrals. These integrals can take some time and effort to evaluate. So good practice to recall all of our integration techniques from 21B. All right, hope this helps.